Today we will do lab 5, so resistors. So resistors in AC circuit. Okay, so now everything now in AC circuit. So this is we just learned before. So for inductor, so it's actance XL, so equals 2 pi FL.
Connor, let me
Yes.
let me just print it. I'm gonna print this one. Just 1 minute, okay?
Okay. Yeah, you can download from the canvas. Yeah.
Okay. I will print it now.
Okay.
Okay,
Yeah.
just 1 minute.
Yes.
And also I open it in 120. I'm gonna go
256.
to the 126 for lab, okay?
Okay. Yeah.
In Zoom also.
Okay. Okay. So XL so equals omega L, then equals 2 pi FL. Okay. F is the frequency. Then for capacitor, so XC equals 1 over omega C, then equals 1 over 2 pi FC. Today we just use resistors actually. Then
Mm.
for series inductor, so LT equals L1 plus L2 plus L3 plus Ln. Parallel inductors, so that's the 1 over LT equals 1 over L1 plus 1 over L2 plus 1 over L3 plus 1 over Ln. Series capacitors, so that's the 1 over CT equals 1 over C1 plus 1 over C2 plus 1 over Cn. Then parallel capacitor, so CT equals C1 plus C2 plus C3. Okay, sorry, this is typo. C3, then plus Cn. Then for sine waveform, so we know RMS value, this one effective value. So VRMS equals 0.707 Vm or equals Vm divided by square root of 2. Then peak to peak value. So VPP equals 2 Vm. Vm is the magnitude of a sine wave. We know magnitude is from the peak value to average. Okay, to average. Okay, so for today's lab, so we will build this one in the Tinkercad. So 100 ohm resistor, 3.3 kilo resistor. We know these two numbers are nominal values. So here we will use these two values. Okay, just make a little bit different. Okay, like yeah. So S is for the sensory. Okay, so this is 102.7 ohm. And for 3.3, so we will use 3.28 kilo ohm. This is a function generator, so 500 hertz. At the beginning, we don't know its magnitude. So we need to adjust the magnitude of the source until the voltage across this resistor is the 4 volt peak to peak value. Okay. Okay, let me build this in Tinkercad. Oh, no, this one. Okay, I already create activity here in the Tinkercad. So create a new one. Okay, so first change name. Okay, great. Then first one, let me drop a breadboard. Then function generator, we need this node, this one. Oops. Function generator. Then we also need oscilloscope. Actually, we need two oscilloscope. This because here we need to measure the voltage first across this 3.3 kilo resistor, right? Measure this one use oscilloscope. In the real lab, we will use the DMM. So this is the digital multimeter, measure the voltage across the 100 ohm resistor. But in Tinkercad, it doesn't has multimeter. So actually, it's the AC voltmeter. In Tinkercad, it can only measure the DC voltage. So here I will also use an oscilloscope, measure the voltage across RS. So totally, so we need two oscilloscope. Okay, so last resistors. Okay, this is okay. So first one is 100 ohm. We need to change it to 1.28. Yeah, 100 and 2.7. Okay, so okay. Then another one. So this is 3.3. So we need to change 3.28. 28. Yeah, 28. Okay, so rotate this one. Let me check which one. Okay, this one is horizontal. Okay, I can rotate this. Let me go down a little bit. Okay, so for this way, so we know these two are connected, right? Then let me check. So last we need the power. So the power, let's connect to the power line, positive power line of the breadboard. So go to red. Then from here, red, go to the top one, just yeah, in case we need a power line on top. Then the last is the negative. So actually this is the ground. So this is black. Similarly, black connect to the black. So just connect these two power lines. Okay, so first one for the function generator, frequency is 500. Then amplitude, we don't know, but offset should be 0. Then this one, let me maybe try one first. Okay. Then sine wave, so sine. Then connection, so this, so connect to the power. So this is positive. Okay, just use different one. So this for connection. Okay. Then here need to connect to the ground, right? Okay. So actually this is the circuit. So circuit will be simple. So positive from the source connect to the 100 ohm resistor. So then goes to the 3.3 kilo resistor, then back to the ground and the negative of the terminal of the source, right? So let me double check. So this is the power positive, 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 then go to 100 ohm resistor, then go to 3.3 kilo ohm resistor, then go to the negative. Okay, back to the source. Okay, so this is the circuit. So circuit is closed now. Last one, so we need to use these two oscilloscope, measure the voltage across the 100 ohm resistor and 3.3 kilo ohm resistor. So positive, this one. So actually we can go to the power because this point connected to the power, right? The negative across the just go to this line. So then the left oscilloscope now across the 100 ohm resistor. Right. Let me move this a little bit. Okay, then second one, so this is negative, so actually go to ground. So because 3.3, this point is connected to the ground, right? Then this one go to this point. Okay, so let me change the color. Okay. Red, black. This is also black. This is red. So again, so when we do the real lab, we cannot put this the two oscilloscope organized in this way. This is because for the real oscilloscope, ground and the ground, negative terminal should connect to the ground. Ground. So actually this means these two are connected. Then this also means, so we can see from here, the current flowing through this line, then here, right? Then this one, then go to 100 ohm resistor, then go to ground. So ground, then back to the ground of the function generator. So this means actually 3.3 kilo ohm resistor is shorted. So for real lab, we cannot do this way. But for this is the simulation. So in theory, he didn't, I think about the negative terminal is ground. He just think about the negative is negative. So we can do this way. But for real lab, we cannot do this way. You can only use the digital multimeter measure the voltage across this resistor. Okay, so let me try. So now ground simulation. Okay, so this one, not right. This is 100. Okay, square wave. Yes, sine wave. Okay. So now let me change. Seems Tinkercad is slow now. Let me change the setting for this one first. So this is 500 hertz. So let me try 1 meter. Okay. Yeah, 1 millisecond is okay. Then we can try 200. 200 millisecond. Okay, yeah, that's great. So we just get the half, right? Oh no, 1 full cycle. So actually we can go to 500. That show one more. Okay. So this also go to 500 millisecond. Okay, so now in the handout, we said before, so we need to adjust the voltage, source voltage until this resistor, the voltage peak to peak value is the 4 volt, 4 volt. Okay. So now we can say totally for this one, the setting from the top to the bottom is the 2 volt. So this means, yeah, totally is 2. Okay. So then this means for each division is just the 0.2 volt, 0.2 volt. Then peak to peak value, so you can see this is almost the maybe 0.2, then 1.2, 2.2, 3.2, 4.2, then this one, so it's another 0.2, so 4.4. So this is 4.4 division times 0.2. So peak to peak value is 8.8. right, is not enough. So we need to change the setting in the function generator. So this is one is peak to peak value. Just remember this. So actually, so we can try 4. Try 4 first. Okay, so now I set the peak value, peak to peak value. So it's 4 in function generator. So in oscilloscope, the right one, so you can see now the setting is the 10 volt from top to the bottom. So this means just 1 volt per division. So totally this is 1, 2, 3, 4. So almost 4 division. That means almost 4 volts peak to peak value, right? Just we can increase a little bit more. So maybe go to, let me try 4.2. Okay, 4.2 I think is enough. Maybe let me try 4.3. Yeah, 4.3 is better. Okay, so 4.3. So now the peak to peak value for this 3.3 kilo resistor is just 4 volt. So 1, 2, 3, 4, 4 divisions. Then times 1 division per 1 volt per division. So totally is 4 volt peak to peak value. Okay, so this is great. Then we need to measure now back to the left oscilloscope. So we need to measure the voltage across the 100 ohm resistor. So this one, so also we need to count division numbers. So this maybe is 0.1. Then let me count. So 1, 2, 3, 4, 5, 6, right? Then almost 6.2. 6.2 divisions. Then times the setting. This is the 200 millivolt. So this means it's just 20 millivolt per division. Then 6.2 times 20. So we get is 124 millivolt. So again, so this is VRS peak to peak value. Yes.
Professor, why did you write that? I think it's 200 millivolt. You write 20 millivolt.
Yeah. So 200 millivolt. This is from the top to the bottom. In the vertical divisions, in vertical direction, so totally is the 10 divisions. So this means for 1 division, so then it's the 200 over 10, so it's the 20 millivolt per division. Okay.
Okay, I got it.
Yeah. So this is the 124 millivolt peak to peak value. So this is different from the handout. So let me go back to the handout. Okay. So in handout, for the real one, I said before, so we need to measure the RMS value first. So this one, VRMS. So VRS, DMM from the multimeter, but we don't have the multimeter in the Tinkercad. So actually, we measure the peak to peak value. So actually, it's this number. So this number, so we can write down in the table. Let me go up a little bit. So for this one, oops. So it's peak to peak value. So it's 124 millivolt. Then from peak to peak value, so we need to go back to the peak value, then go back to the VRS. That's the RMS value. Okay, so we need to use another way. So peak to peak value, go to peak value. So this is very simple. This is the peak to peak value. So we know it's 124 millivolt. Then peak value, so we know it's half of the peak to peak value, right? So that's the peak to peak divided by 2. So this is the 62 millivolt. So that's down here, 62 millivolt. Then DMM value from the digital multimeter, this is the VRMS value. VRMS value, so this is the peak value divided by square root of 2. Okay, so that's the 62 over square root of 2. Then this number, so 62 divided by square root of 2. So 43.84. So for this one, the better keep the 2 digits after point. Okay. So 43.84 millivolt. Okay, so we need to use then this value to get the I peak to peak value. This is the series series circuit, right? Then for the I peak to peak value, let me write down this first. So we know we can use the Ohm's law, right? Okay, let's keep going down. So when we keep it down, so we will, then peak to peak value. So for the current, then I peak to peak value equals VRS peak to peak value divided by RS. Here, RS, we need to use this, the measured value is this number, okay? Okay, so calculate here. Then we will get, so it's the peak to peak value divided by RS, then equals 124 divided by 100 and 2.7. Then you will get a number, right? Then put in this place, peak to peak value. Okay, so this one I don't do calculation. So actually, when you do the lab, so you can do this. Then the last step, so is this one. So determine the resistance of the resistor R from this formula. It's because R nominal value is this. Okay, just a moment. Let's go to Tinkercad. So this one, the nominal value is 3.3, right? Then for this one, we already get the current from here number. Then we know the voltage across this resistor 3.3 is 4 volt. So from Ohm's law, so we can get its resistance. So this one. Then after finish calculation, put the number in this place. Okay, this one. Then this after this one, so you get then compare the value. This is the measured value from the calculation value with this measured value should be close. These two value. Okay. If not close, so double check your the measurement and also your calculation. Okay, so this is this one. Then after finish the first circuit, then you need to add one more. Okay, let me erase everything. So add one more resistor, 1.2 kilo ohm resistor, still in series. Okay. Then for this one, so we need to measure the voltage across the R1 and R2 is the 4 volt peak to peak value. 4 volt peak to peak value. Okay. So again, so adjust the source voltage until the voltage across R1 and R2 is the 4 volt peak to peak value. Then other price is the same. After get this one, then also, get the peak to peak value, then back get the total, no, the voltage across the 100 ohm resistor. This also from the oscilloscope in here. Then this one, so the calculation, so this is the total resistance. So just add this, actually these 3 numbers together. Don't forget kilo, that's for 1,000. Okay, don't forget this when you do addition. Then from VRS peak to peak value, then you can get the current peak to peak value. Then we can get the RT, this one, just 4 volt divided by the current, right? So this is the total. Actually, this is not the total current. So this is the current for R1 and R2, total current of R1 and R2. Right? Okay. Oh, okay, sorry. So for this RT is also the total current of the 1.2 and the 3.3, not includes this 100 ohm resistor. Okay. So for this one, okay, so this is the lab in the Tinkercad. Yes? Yes? Sample, you are mute.
Oh, I'm sorry.
Yeah.
So table 3.2. So there is RT down.
Yeah,
RT.
yeah, this
This
RT,
RT.
yeah, just,
We're gonna add this, right?
yeah,
We're gonna just
this,
add this.
use right numbers. Right numbers assume is the measured value. It's different from the nominal values.
And for the other RT, we're gonna calculate or we're gonna measure it.
This is calculated.
The last RT.
Last RT also from calculation, from the Ohm's law. So VRT divided by I.
Okay.
Okay, so this one is in the Tinkercad. So just a moment. Okay, so you will do this in Tinkercad. Then just a moment. I think I didn't open this. So I also do this simulation in the MathSim. I said it before. This one. So MathSim, so actually it has the multimeter. So for this one, so this is the multimeter. This is the oscilloscope. I showed this to you before. Then this is the function generator. Then, so for this one, so let me run this first. So here, so you can see the voltage across the 3.3 kilo ohm resistor. So I use the nominal value here. Actually, I can change it to the measured value. Then this is the 4 volt peak to peak value because the setting, so setting is the 1 volt per division. So 1, 2, 3, 4. So this is the 4 volt peak to peak value. Then for the multimeter, so you can see this is 41.594 millivolt. So this is the RMS value. So for this one from the multimeter, so this is the VRMS value. So it's the 41.4594 millivolt. Then from this one, so we can get the peak value or magnitude first. Then this is the square root times VRMS. Then the last one, so we can get the peak to peak value is the 2 times peak value. then we can use Ohm's law get the current. So in multi-sim, so we can do the steps exactly like in the handout. In TinkTech, so it's doesn't have the multimeter, so we have to use the oscilloscope measure the voltage across the resistor. Okay, so this one. Then no, not this one. Okay, so then this is for the part from step 5. So 108 kilo ohm resistor, 1.2 kilo ohm, then 3.3 kilo ohm resistor. Then this is also multimeter. Then run this one. We still need the voltage across these two resistors is 4 volt peak to peak value. So this is the 4. Then this number, so now it's changed. So it's 30.743 millivolt. Okay. Again, so this is the RMS value. So you can see this is the AC. So this means this multimeter can measure the AC voltage. If we change to the DC, so you can see this number will change. Okay. Okay, so this is for this one. Yes. Yeah.
Professor, we don't have multimeter. That is why we have used the two
Yeah,
of.
you just use Tinkercad. Okay. You just use Tinkercad. Yeah, because you don't have this one. Okay. And just one moment, let me show the multimeter here to you. Let's show why we currently use multimeter. So this is the multimeter. Then I said before, this one can only measure the DC voltage. Go here. For the sine wave, if for the DC voltage, we know the average, so it's just 0, right? So when we start simulation, so you can see this number just keep us 0. So this is the reason we have to use the oscilloscope in the Tinkercad. Okay. Okay, so now you can start now. Yeah. Let me stop the record.